Welcome, everyone. This is Chris Fregly, and I'm here with a bunch of awesome speakers that I've been able to procure for the month of February. Today, happy President's Day to all the US folks. It's the day we get to celebrate Donald Trump for whatever that means to you, positive or negative. Happy President's Day. The best thing is you probably have today off. So thank you for dialing in on your day off if you're not out and about hiking. It's raining pretty badly here in the Bay Area. So probably not outside at 9 in the morning today if you're out west here. We've got great talks. I'm actually going to give up my little intro slot here for a talk by Stan from Nebius. And Nebius is a neo cloud provider. They've got Token Factory. They've got all kinds of cool stuff that Stan's going to talk about. He's also going to talk about this new course that's about performance engineering in AI. So that'll be really exciting. I caught wind of it a couple weeks ago and was really excited to get them out here on the meetup to talk about this. I think the initial one's going to be in the UK in person, but they do plan to expand to other places. I'll give a very brief, I might actually defer mine to the end because Riccardo, who is supposed to speak towards the end, is actually in Europe, and I want to make sure he has time because it's like 7 o'clock his time. So he'll probably go first, and then I'll finish up with a quick. I've been playing around. Yeah, obviously, I wrote a book here called AI Systems Performance Engineering, and spent quite a lot of time hacking on these kernels myself. The year 2026, I've decided to not write a single line of code. So I built out a GitHub. This is actually the GitHub for the book, which is documented in the book and pretty easy to find. AI Performance Engineering off of C. Fregly, and I've got a whole bunch of MCP tools here that you can pull into your AI assistant and apply all of the techniques that are described in the book. So really, really cool. I also, of course, everyone's hopping on the OpenClaw, MoltBot, ClawdBot craziness. So I actually got that to work. So I can, from WhatsApp here, or from Telegram, or from even my text messages with like iMessage, I can launch CUDA kernel optimization. So that's kind of cool here. It's asking some follow-up questions that I don't have time to answer right now. And then we'll have a really good talk about NVFP4 and low precision numerics, specifically on the NVIDIA Blackwell chip, likely the B200, I assume. So we're going to let Riccardo talk, and then we'll flip the order of talk 1 and 2. Stan, do you want to take over?
Yeah, thanks a lot, Chris, for this amazing opportunity. So I'm really happy to pitch our course here today. Could you please stop
I have to
sharing?
stop the share. Yeah.
Yeah.
And quick reminder that we do post everything to YouTube, and I will post the link to the channel here. And cool. Stop the share. It's all you.
Yeah, thanks a lot. Yeah, my name's Stan. I'm the AI program lead at Nebius Academy, and I'm really thrilled to pitch our upcoming AI performance engineering course today. First of all, a couple of words about Nebius. So Chris has already said a few words. I'll add a bit. So indeed, Nebius is a neo cloud, but more broadly, Nebius is the vertical company. So from top to bottom, we built everything to power AI. So of course, AI needs GPUs. So first of all, Nebius is a GPU cloud with the fastest and the most powerful GPUs from NVIDIA in data centers all around the globe. But on top of that, we have many different services like Kubernetes, fast storage, networking, whatever is needed to create really reliable AI infrastructure. Then, of course, we know that running and customizing AI models is crucial, but at the same time, it's hard. So to spare companies that don't want to go deep into technical stuff, this effort, so we offer inference and fine-tuning as a service in our Token Factory product. But of course, AI won't work without people. Well, people who can turn tokens into real business value, without people who can set up really efficient inference and training. And for that, we have Nebius Academy. So this is the way we contribute to the community and help everyone be better with us. And so one of the course so we are launching this spring is the free in-person program AI Performance Engineering in London, which will start on March 18th, so just a month from now. So let me say a couple of words about what's inside. So in this program, we basically want to train AI performance engineers, people who can uh, set up efficient inference and training of AI models and, first of all, of LLMs. And so this goal, it explains the structure of the program. So you see there are 14 rows here, so there are 14 weeks. And 2 columns, these are 2 classes per week, Wednesday evening and Saturday afternoon. And so we have at every point in time 2 courses running parallel, forming kind of 2 streams. So one stream is about designing, building, scaling AI systems. So it starts from how to design and build an agent, and we will also reference the OpenClaw craziness, which Chris mentioned. And after that, so we'll start discussing how to like deploy, scale it in cloud. In parallel, so the second stream, it aims towards performance engineering, and for that, we need to understand what's under the hood of LLMs. So we have quite a strong module dedicated for that. So what are transformers? What is inside? What are the components of today's LLMs, and how LLM inference actually happens? And armed with this knowledge, so you will be able to explore efficient inference and training strategies on very different levels. So from writing custom CUDA kernels to speculative decoding, including, of course, all the flash attention, quantization, etc. In the middle, and as for training, of course, it's model parallel, data parallel, context parallel, so whatever cool strategies we now have, and like kind of crowning this, there is a LLM post training module with a bit of SFT and quite a lot of reinforcement learning techniques for LLM post training. So this program is very hands-on, so there'll be lots of home tasks, code demonstrations, so real experimentation on Nebius infrastructure under the guidance of experts from Nebius, OpenAI, evidently AI, who really do this stuff every day. So if you're skilled in Python, you know some things about machine learning, and you're probably familiar with the cloud, and you want to like dive deeper, and you are in London, so I guess this course might be a good match for you. So yeah, please join. I'll be happy to see you at the course. So yeah, please register. So the course starts in a month.
Any chance for a online version? Someone's asking. Which a couple
Uh,
people ask.
so kind of we don't have a dedicated online version, so we'll be like filming recording what the lectures, so
Cool.
probably that might fit. So anyway, so f feel free to write me in LinkedIn, Stan Fedotov. So yeah,
Great. I actually, Stan, you'll find this interesting. Let me grab the screen share here. And I actually did a survey when I wrote the book. I have about 300 responses about what people would be looking for. So looks like the number one here is learn best practices for new AI system development. The context here is I've been thinking about putting together a course as well because of I've got a lot of book content, which is why I was really excited when I heard from you guys because it seems like the perfect course. Um, yeah, understanding AI bottlenecks, explore tools and techniques, networking with other performance engineers. Let's see. And then the types of people that were responding, there's a lot of ML engineers, of course, software engineers, a lot of students, a lot of data scientists. So that's kind of fun. Medium experience with AI systems. So that's a good breakdown. You always kind of want to target the middle of the group that you have. Model optimization, hardware acceleration are pretty high up here. Data pipeline optimization. This was a multi-select, so I think they could select a bunch of things here. So we got decent signal there. And then this actually maps to the book, the chapters of the book, and it looks like most people were interested in profiling and tuning. Memory access patterns. That's right. That's a very important one. And of course, inference, chapters 17 and 18 of my book cover VLLM profiling and tuning, KV cache, DISAG, PD, and yeah. And then let's see some other. Oh, here's the breakdown. Looks like 41% wanted online self-paced, which is interesting. Mix of self-paced and live. And let's see, preferred more than 5 days, kind of a multi-week program. So that's what you folks have done, right, Stan? You guys have a 14-week program, which is good. Good pace gives people time to kind of absorb the material and try things out. And um, I tend to lean more towards 1 day type of thing, or even 2 days. Because there's so much content here, you kind of have to spread it out. Here's some specific frameworks. Looks like SGLang came up a little bit more than I had thought. So I'm seeing a little upsurge in that. And yeah. So okay. Why
yeah,
don't we
that's
get
insightful. Yeah, thanks a lot. Thanks everyone.
yeah.
Thank you, Chris.
Thanks, Stan. Yeah, look forward to it. I'm going to dial into that for sure. So hopefully I can get a ticket. um, Riccardo, do you want to take it away? Let me stop my
Yep.
share. And don't forget to introduce yourself, talk about Verda, and let us know what you've been up to.
Uh, can you see my screen?
Perfectly. Yep.
Yep. Hi everyone, I'm Riccardo. I'm a machine learning engineer at Verda. So first of all, I will give you a little bit of context of who we are. Verda is a neo cloud provider. We are based in Finland, so we are in Europe. And today, like my talk will be on low precision numerics. So I will try to guide you on what was like kind of the path that drove NVIDIA to push that much into low precision numerics, and especially how do they end up like developing the NVFP4, which is their own proprietary low precision 4-bit floating point format for their latest Blackwell architecture. So before like diving in this low precision presentation, which may also maybe like maybe you wonder why like a cloud company is even interested in this sort of low precision numerics. First of all, so like let's give you a little bit more context on Verda. Again, like we are a AI cloud provider, and one thing which is different from neo clouds compared to previous cloud companies is that right now, given the huge focus on AI, we needed to create some hyperscale, some clusters that are like created in mind, having in mind GPU workloads. So in this context, is important to squeeze out as much performance as possible from the GPUs, because compared to the previous generation of cloud providers, where it was important the time that the programmer was spending on the cloud, here is important to not waste a lot of GPU time, because that's the costly part of the renting services on the cloud. Plus, like, it's very important, we are really committed also in green energy, such that like in Finland we have like our data centers are here in Europe, and we are also like heavily involved in getting better performance in terms of power consumption and this sort of stuff. Finally, also another important thing for our customers is that we are really being a European company, we have to be under the GDPR, so like we are compliant with GDPR, and we provide services to make sovereign AI I think also in Europe. All of that to say that like to create a cloud company you need to provide all these kind of services, so this modern architecture that gives you access to GPU workloads, and you need all these different blocks like object storage, networking, security. So like it's very important that the whole stack is created with in mind this sort of workloads, such that you can again get the better performance and use like this very complicated hardware that are these GPUs nowadays. So one interesting thing, which is like that leads us to the core of this talk, is what happened in the last years and why is important, why low precision was important in this sense. So if we are looking at the evolution of the inference performance of the NVIDIA GPU hardware over the years, this is a slide that I have adapted from this talk from Bill Daly, which is one of the chief scientists at NVIDIA. And as you can see here, on the x-axis we have the time, so this covers like from 2012 to 2024, when the Blackwell GPUs have been like released by NVIDIA. And over these 12 years there's been like a growth in computation which is like 5000x. So like we started from like a certain number of tera operation per second over 2012, and we grow like in a very exponential manner. So if we see this plot in log scale, so here this time on the y-axis we are on log scale, we see that over the different releases of GPUs, NVIDIA has constantly provided higher and higher compute for their GPUs. So starting from 2012, where we had like the Kepler series of GPUs, which was like kind of low, and NVIDIA was using this 28 nanometer fab production for their chips, and they squeezed also in the physical sense. They started like creating smaller and smaller chips until like the latest per GPU, so like the Hopper ones and the Blackwell ones, where they reached the 5 nanometers for the production of the chips. But like there are also other things that happen over time. So as you can see here, like on the first years, NVIDIA used like very large precision numbers. So like we started like with the classic IEEE standardized floating point 32, floating point 16, then with the advent of like the Ampere GPUs, NVIDIA also started introducing sparsity at hardware level, where like the GPU could already at hardware level detect some sparsity patterns in the gem operation, and then using particular instruction sets that they created, you could improve the performance of the hardware. Then like moving to the latest GPUs, we had an even larger improvement there, because like with the Hopper, NVIDIA had released also some FP8 hardware support, and with the latest Blackwell GPUs, NVIDIA pushed that even farther to the NVFP4, meaning that like they are using for each number that is used in the model that you are training, that you are using at inference, you are using just 4 bits to represent each one of the weights or the activations or other parts of your ML structure. Then another thing, this is kind of another thing that is very important for NVIDIA, is that they do not just like add the they weren't just pushing just one chip, so just the GPU, but they were also thinking in terms of scaling at the scale of the rack. So with the latest GB300, which are these new machines that NVIDIA released, which are the Grace Blackwell 300 machines, they are here you can see the name also have this NVL72. This is basically an entire rack of GPUs with 72 GPUs all connected all together in a single rack, and this allows to see the whole rack as if it was a single GPU, or at least that's what NVIDIA has in mind. We at Verda, we are currently deploying all the Blackwell architecture, so we have B200, B300, and also like previous generation of GPUs as H100, A100, and like similar stuff. And we are also right now deploying our first GB300 that will be available soon, and they are kind of central in the view of NVIDIA to scale first inside and at the rack scale, and then scale out over multiple racks, creating more and more powerful data center level architectures. So we were talking a lot about this 5000x improvement of performance, but then if we want to kind of dissect where all these increases were coming from, we will be surprised to see that the process on how many transistors we were squeezing inside the GPUs is actually not that big in terms of impact. So like the improvement in compute that the GPU got in terms of improving the quality and the squeezing the physics of how many transistors we could put for millimeter square in a chip is actually quite tiny compared to other parts of the other improvements that NVIDIA brought to those chips. For instance, like if we look here, I put both, I kind of dissected in all the different parts. We can see that the larger improvement has come not from process, not from instructions, but from the number representation that was used in the model. Why so? Because like if we squeeze the number of bits that we are using, we can put more hardware doing actual useful computation, because we are squeezing, we require less hardware to do this computation, but then we are also pushing down the power consumption of the chips. Then we can squeeze more weights into a single GPU, because all the weights are also quantized. Finally, another interesting part that one needs to take into account in this sense is also that in the recent years we had a lot of hardware software core design, meaning that we start using algorithms that had in mind how the hardware of the GPU was built. So we have flash attention, flash attention 2, flash attention 3, and flash attention 4, and so on, that following the development of the hardware provided the actual user, so the end user, maybe not directly because you are writing your PyTorch code, and then at some point the compiler will detect which flash attention is better for your own hardware. But at the end of the day, like having in mind what these hardware are capable to is quite important also to squeeze as much performance as possible from the GPUs. So if we want to like dive a little bit more now on the core of this presentation, which is NVFP4. So like first of all, I already started giving you a little bit of an idea of what are the key reasons why the low precision is important, but I will give you more as we go through the presentation. Then I will introduce you NVFP4 and why it's different from the other low precision format, and finally why the NVIDIA Blackwell enabled this and why this is important basically. So let's do first a step back and see a little bit of the history of what was the numerics that has been used by the AI field in general, both in industry and academia over the years, and what happened. So like if we look back at the first early deep learning models, we will see that the 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 first architectures, the first models like AlexNet, DAMNet were written in CUDA usually, and they were using FP32. The reason being that like the GPUs weren't meant for with AI in mind back at the time, and so there was a lot of waste, let's say, of the use of the float of the numerics to represent these the weights of the architecture, because like in ML is not as important as in other HPC engineering or scientific approaches to get all these precision. So FP32 is a little bit of an overkill because your weights can be quantized quite a lot, and that provides you a lot of like good positive effects in your workload in general. So over the time we start shrinking the data format, so they start realizing that FP32 again was an overkill. So in the next year they start like popping up different mixed precision training, because like once you move into low precision, you are not training anymore in a simple way, but you need to come up with a sort of recipe. This recipe will tell you how you need to store the different elements of your training stuff. So like there will be the gradients that maybe have been computed in FP32, the master weights that again are stored in FP32, some parts of the network that instead are in FP16. So all these techniques were slowly merged into the main frameworks, so like PyTorch, Caffe, Theano at the time, and then there was like another realization, like at Google, especially when they were like designing their own hardware, so the TPUs, they start using a different format, which was using the same exponent as FP32 to maintain the range of numbers that could have been represented with that floating point format, but then using less bits for precision. In that way, when you were representing the numbers in your neural network, you were more interested not in like getting a very accurate representation of the number, but kind of get the right range of numbers. And this is important because it tells us that the GPUs, the neural networks are kind of robust in this sense. We can squeeze, throw away a little bit of precision and just get the right let's say range of numbers you want to represent. After that, also NVIDIA introduced like an hardware support for the BF16, and with the Hopper architecture, NVIDIA pushed that also to FP8. In 2023, there was like a sort of like the main producer of chips like Intel, AMD, NVIDIA got together with this open compute project that introduced these microscaling formats. So they use a bunch of they proposed a standard for some new formats, basically MXFP8, MXFP6, and MXFP4. The difference from the regular FP8 is that instead of doing a scaling on the whole tensor that you store in memory, you break this tensor in smaller chunks, and you use a different scaling for each one of these chunks. Finally, we arrive with the NVFP4, which are in the latest NVIDIA hardware. They differ from the MXFP4, as I will give you more detail later on, and this particular hardware support is again only available on the Blackwell and gives the user at hardware level some improvements in the microscaling compared to the MX format. So why FP4 training is important? If we have a look at the trends of the models that have been trained by Frontier Labs and LLM in general, we have seen a kind of steady increase over the years. That if we this image comes from a an article from Epoch AI, and they shown that like if you look at the frontiers model over the last years, we have seen an increase in the number of parameters and the flops needed to train these models that have been like 5x per year. So these are required both smaller data formats, because like you want to have the model to be processed faster, like your answer needs to go faster through the hardware, and then you want to have an high throughput of the number of tokens that your model will produce every second. So in this sense, NVIDIA has kind of did its own bet of like pushing even more for these architectures to provide smaller data formats, again as this FP4, and provide better support for the FP8, providing also some tensor cores. So in this case, as I was saying, it's not only that NVIDIA is using smaller data formats, but they are also developing the hardware to handle these smaller numbers and provide better performance on the GPUs. So, step back again. This time I want to cover a little bit more on the floating point basics. So when we are representing, when we are dealing with neural networks, what we are actually doing is like compute some sort of function. This sort of function, which is like tunable, because we have the weights that are like, this is a parameterized function that with weights that we want to represent on our machine. Since our machine is not that good at infinite range and infinite precision. What does it mean? First of all, like if we were just using numbers, they will sit on the real number 9. So in the actual real number 9, we can represent all the numbers that we want. So very small values, very big values, and this gives us like the range of values that we can represent. Then if we zoom in into the real number and into the real number line, we have an infinite precision, meaning that we can also pick all the small numbers between two numbers. So if we go between -1 and -0.8, we will again get infinite numbers there. But we cannot do that in a real machine, because first of all we have a finite memory, so we cannot store like very infinite numbers, and also the silicon area that we have in our chip is finite. So even if we wanted to use a very high precision, a very high range, that will even if we want to, like, we commit to do that, the fact that we are dealing with a finite thing will mean that we will have to wait a lot of time, which is not something that we want to do. So what we always did when we deal with machine is that we need a different number representation. That's the reason we have integer representation, floating point representation, and in the case of floating point, the thing is that like we are sampling the real number line in a sort of logarithmic way, where we are picking more number in smaller ranges. So we will pick more numbers between 0.125 and 0.25, and we will instead like spread out the samples more and more as our range increase. When we refer to floating point, we usually represent the format with this notation E, X, and Y, where E are the bits for the exponent, which will give us the dynamic range, so how big or small we can zoom into the numbers that we want to represent, and the mantissa will instead give us the precision. So if we put everything together, we will be using 1 bit for the sign. So this formula here is telling us how to map our binary representation, so the bits that are sitting in memory, into a base 10 number. So the bits the sign bit will be the exponent of this -1. So if it's 0, we will have a positive number. If it's a 1, we will have a negative number. Then we will use the bits for the mantissa. Here I'm skipping a bit. These are just is not considering the subnormal representation for floating numbers, which will cover basically all the different exceptional, like particular numbers that we need to represent, like nonce or infinite, the sort of values that have we will require some additional time that we don't have. So we will focus mostly here on the normal representation, which assumes that the first bit, we will have a 1 bit always set on, and then we will use the bits for the mantis after that. Then we also have this exponent bias, which is a clever trick to make sure that the exponent is always an unsigned int number, which makes a lot of sense because like saves you like some bits and is easier to deal with at hardware level. So if we look, for instance, here, this is an example to make sure that everything is clear. This will be like this base 10 number, so 6.510. If we wanted to represent that as an FP16 number, which is using 5 bits for the exponents and 10 bits for the mantissa, this is the actual representation. So we will have the sign bit, which is 0, meaning because the number is positive, the exponent bit here, which is here is 16 minus is 17, so the green part is 17. We have the exponent bias, which is 15, again for the represent this number as an unsigned integer, and the bits for the mantissa are you substitute that also in the mantissa part, and if we put together and translate this into actual power of 2, you will have 1 which is coming from the sign, then the first one which is coming from the normal floating point representation, and then the 2 sign which comes with these 2 numbers that are coming from the mantissa. So you are summing 2 to the power of the -1, 2 to the power of -3, and you multiply that by the exponent. Putting all this together, you get the number that you actually have stored in memory. Zooming out, if you look at like visually what is happening here, we started from an FP32 number, which again use, as the number says, 32 bits for representing each of the numbers in our model, which is using 8 bits for the exponent and 23 for the mantissa. Then we switched to FP16, which was using 5 bits for the exponent and 10 for the mantissa. Then with the BF16, Google brain scientists decided that it was a clever idea to use a larger exponent to increase the dynamic range of the number. Then with FP8 we start using some tensor scaling factors for basically you want to avoid, when you are squeezing your representation to lower precision, you want to avoid overflow and underflow there. So you need to kind of move the range of values in the right scale such that the binaries that you can represent with your floating point representation are good enough to represent all the values that you want to have in your computation. The MX format moves from a single tensor scaling factor to 32 block level scaling factor. What does this mean? It means that when we are storing a tensor in memory, every 32 numbers that we are storing, so we will have the first number, which will be 8 bits, then some other numbers, some other numbers, some other numbers. Once we got 32 of them, we are scaling them by an E8M0 number. So this is basically saying we will scale this block of 32 floating points number using just the exponent of a FP32 number. So this is kind of already better than the simple FP8 because you are not scaling, like you are less sensitive to outliers with the tensor, which will happen with the tensor scaling factor. But since you are not, you're using basically an integer to represent the scale, you will move in a sort of like at powers of 2. Here, while with the NVFP4, the changes compared to the MXFP4 here is that we will have 2 things. First of all, the number of elements in the block level scaling is no more 32, but is 16, and then is using a different format. A different format for the scale is not an E8M0, but is an E4M3, meaning that the scaling factor is no more like just a power of 2, but it can be like fractional, and so like it is kind of increasing more the precision of the values of the scale, but then it's also combining to a true level scaling, because we will also have an FP32 tensor scaling factor, which is again important to avoid the training to diverge and the basically throw away all the computation that you're doing. When we use these low precision techniques, what we are actually doing is that we are quantizing our model. So we are trying to squeeze into less bits the actual numbers that we wanted to represent in our function. So there are different ways people have come up to do this model quantization. The first one is doing post-training quantization. What happens here is that you train your model, so you have your final train model with all your nice weights, and what you actually want to do is that, like, to make the model run faster and perform better, getting high throughput, what you do is that you take your weight and sometimes also the activation, and you map them, like you quantize them into low precision formats. In this way, you do not need any training data. You don't need even like any training hardware, but there is a trade-off here, which is like it may drop the performance that you got in your initial model. So you will get a smaller model, but this model will have worse performance. Again, this is just at inference time, so we are not touching the model at training time, never in this type of techniques. But again, if you want to get this performance drop, but if you want to avoid that and like still get a model which is like high performant, what you need to do is start also doing that at training time. So the first approach is doing quantization aware training. What does it mean is that, like, also when you are doing the training, the forward pass of your model will be quantized. So this is basically shifting the problem from like doing the quantization after you train the model into like saying, okay, let the model figure out how to avoid dropping performance by already incorporating into the training forward, which is quantized, in such a way that the weights will be tuned to counteract the loss in performance that you get from the quantization. Finally, the most important part, like the one that we are really interested in, is this quantized training. So quantized training takes all of we said so far, and we puts quantization everywhere. Basically, we are putting quantization in the neural forward pass. We are quantizing the backward parts of the network, so we get also an improvement in performance when we are computing the gradients for the model, and then it can also be used in the distribute collective. So like when we are transferring data, which could also be like the weights of the model if we are doing some very complicated parallelization techniques like FSDP or this sort of stuff, we may want to not move over the network weights that are stored in a very high precision format, but we want to use this quantized format to reduce the amount of data which is moving across the network. So the question may be right now, okay, everything Riccardo said so far is kind of nice, seems really cool, but does this thing really works in practice? Or better, how is it even possible that using just these 16 values is enough to represent all the weights, all the activation, all the stuff that we need to train a model in practice? Well, the answer is no. See, these 16 values are not enough as they are. You need, as I said before, a recipe here. You need to be aware that like all these low precision comes at a price, and this price is that you need to put together a couple of tricks to make everything to work. First of all, in terms of hardware performance, as I was mentioning earlier, NVFP4 makes some different choices compared to the micro format FP4, so from the MX FP4. So these tricks that again, everything I'm saying here is already happening at hardware level. So there is like when the model is performing the GEMS operation, there will be some dedicated hardware doing this sort of scaling the numbers to the right scale again, to the right range. What's happening here is that like every 16 numbers. So here on top, like there is a zoom of this block of NVFP4 number. Here we can see that we have like the maximum of this block, which is 6, which is the higher number that we can represent with this FP4 format. Actually, there are like some tricks again in the literature using this. It's called 6 versus 4 approach, where depending on how you scale, instead of scaling between -6 and 6, there are some improvements if instead of doing that you scale the numbers that you could represent in this NVFP4 format between -4 and 4. But this is another story. So what's happening here is that you have these 16 FP4 elements, and each of them are scaled by this FP8 scaling factor. Again, this FP8 scaling factor is, as you can tell here, is not an E8 M0, but is a fractional one using also 3 bits for the mantissa. So you will be storing basically all your weights plus some metadata here, which are like the scaling factors, and also a tensor level scaling factor, which is a full FP32 numbers. So what's the reason why we are interested in doing so? Because like we want to increase the accuracy of outliers, which is very key and important for training LLMs, and we also want to minimize the values that get squeezed to 0, meaning that if we use a very large number of elements, as the MXFP4 is doing, there is a higher chance that you will squeeze, if you get like this outlier, this 6, and then all the other numbers are around 0, your scaling will make so that like all the small values will be squeezed to 0, which is like very bad for your model training. So this is again some reason why doing so is important. So like if you look at this NVFP4, this is a visualization from an NVIDIA presentation where is showing in the GIF that you have like your 4-bit number, which just has like a bit for the sine, 2 bits for the exponent, and 1 for the mantissa. They are aggregated in blocks of 16 values, and then you will have block scaling for each of these 16 values block, and then a larger one for the FP32, which again is meant to move the to prevent overflow and put the kind of align the numbers that we are using to the scale of the numbers that we want to represent to avoid numerical problems. So what's happening when we do this NVFP4 recipe? We will have 2 stages in the training. First of all, we will have the forward pass, then we want to compute the gradient, do the back propagation, and then update our weights and do that such that we minimize the loss. So when this is happening, we are computing these 2 passes. Basically, usually when you are interested in just quantize-aware training or the post-training quantization, you will only focus on the forward pass. The difficult part usually is when you need to also add the kernels for the backward pass, because you have to take in mind like many things. For instance, here in the NVFP4, what the NVIDIA engineers found out is that it was really important for them to provide a 2D scaling. What do I mean? There was a problem. The issue is that like when you are quantizing the weights, the quantization, and you apply this quantization in the forward pass, and then you apply the same quantization to the transpose of the matrix in the backward pass, what is happening is that these 2 things are not the same operation. And to counteract and this is because like you are trying in general with the quantization approach to represent blocks that live in a 1D dimension, which is not the matrix that we want to represent. So like if you, instead of doing that, like you do the scaling in 2D blocks of 16 times 16 blocks, when you are doing the quantization over the weights, you provide a quick and effective solution for this transpose issue that you get otherwise in training with low precision. Then another technique which is used with low precision and that you have to keep in mind is stochastic rounding. So when you are like rounding your numbers, you will round with a certain probability to the floor or like to the let's say bigger or smaller closest representation that you have of your model with a certain probability, which depends on how large is the difference between the value that you want to represent and the one that you can actually represent with your data format. This is done in such a way that on expectation, the number that you are representing is closer to the real value that you want to have. Finally, another technique that you have to put into this recipe is the random Hadamard transform. Basically, when you are computing the forward pass of LLMs, you want to have put a lot of attention into outliers, because those may be like the important bits into your LLM prompt or the actual answer that you are generating that contains a lot of information. So if you since the outliers will be squeezed a lot with this quantization, you want to counteract that, and to do that, like what is happening here with this random Hadamard transform is that you are applying a orthogonal transformation you are basically rotating your activation such that they look as much Gaussian as possible, and you do that also with a random transform such that you avoid some kind of systematic if there was a sort of a recurring pattern in how these outliers are presented and you just do an Hadamard transform, this won't kind of counteract this effect. By doing by applying this random Hadamard transform, what is happening is that what you can see on the right top panel, which is that basically in the red distribution is the original one. After the transform, the model, the activation kind of get a little bit more Gaussian, and they distribute more, they have more mass around zero, and this is better for the training stability of the model. So it's kind of interesting that when basically if you were applying the Hadamard transform, you need to define these H matrices, which are like matrices of like minus and plus one. With the random Hadamard transform, you are also introducing this diagonal S, where S is a vector of minus and plus one. And if you have a look at the transformer engine code that NVIDIA has released for the NVFP4 training, they are like setting this S vector into like some weird and magic tensor that we don't know why they pick, but apparently it works. So they had also like this meme here in the comments, which is quite fun. So putting all together, this is kind of a big overview of what's happening on the top part, and this coming from the paper that NVIDIA released on NVFP4. When you are training with NVFP4 on your forward pass, which are like these three rectangles in the scheme on the upper part, you have your activation coming from the previous layer. They get quantized into NVFP4, so you go from BF16 numbers into NVFP4 numbers. Then they got like they go through like GEM, so generalized matrix multiplication, which is done into the NVFP4 tensor cores in the Blackwell architecture, that then gets accumulated into BF16 and becomes the activation for the follow-up layer. When you are instead computing the gradient for the backpropagation, when doing the backpropagation to compute the gradient, basically you need to apply all the different tricks that I mentioned before. So you need to apply the 2D transpose for the 2D block quantization for the weights. Then you also need to apply the Hadamard transform to squeeze, like to kind of align better the distribution of the activation to a Gaussian one, so an isotropic Gaussian one. And yeah, so when you get the activations from the activation gradients from the previous layer, what is happening is that you apply the Hadamard transform, you quantize with stochastic rounding, and then you compute the weight gradients with again a gem NVFP4 kernel, which will produce a BF16 gradient, which will be used by the optimizer to update the master weights of the neural network. So all of this together may seem super complicated, and is one of, again, it's kind of you can play around on many of these building blocks, which is what is happening in the literature. So depending on how you're applying these different blocks, how you squeeze the performance of each one of these different blocks, or even how you choose how you quantize the values in your neural network, will affect, of course, the performance and also the quality of your model. So in terms of results, what the paper from NVIDIA showed is that they were able to basically match training with FP8 representation for the weight. There is a catch here. The NVIDIA paper were actually using their own Nemotron model, which is a sort of hybrid model using both self-attention layers and Mamba layers. So there is like a sort of so it's very specific to that model. Different papers are focusing also on Llama model and similar stuff. And on the right side here, instead you can see how a sort of ablation. So what they did here, they let the model train with NVFP4 for a while, and then they start switching on and off some of the other building blocks. As we can see in this small blob here, when you use the full recipe, the model is quite stable, so it's not that different from an FP8 loss. When you start, first of all, like if you disable the stochastic rounding, the model, the loss is quite different and the model starts diverging. Same happens, but slightly less if you remove the random Harman transform, while it seems that the model is a little bit more robust to the 2D scaling, and some sort of like the red line is that they are also using usually they are keeping the last layer of their model to be at higher precision because it works better. So like why it's one may wonder why it's more robust for the yellow line. So if you remove the 2D scaling, I can give you probably a kind of intuition for that, which is that when you are computing the gradient, you are kind of trying to get the right direction on where to move your weight, and these if you just remove this problem with the transpose part, which is what the 2D scaling is trying to solve, you are not that far off in terms of direction where you're updating the model weight, so the effect in the training is less evident from, like, I don't know, the removing the stochastic rounding, which is like instead introducing a very strong bias in the quantization. So all that put together translates, according to NVIDIA, into like a 2x improvement in throughput for GB200, which becomes 3x if you are using instead a GB300 compared to an FP8 training. And this also basically halves the memory needed for your weights, because like if you are using just FP8 weights and you move to NVFP4, you're using half of the bits for that, which is translates again in larger model that can fit in your GPU. So all of this to say that like NVFP4 is this new proprietary NVIDIA format. You need some Blackwell hardware to use that, so like you are bounded to use B300, GB300, B200, GB200, or even the RTX Pro 6000. And the reason you want to use that is usually that you are serving very large models. If you focus on B300 and B200, you usually have like a very large, and also the GB variant, you have a very large VRAM there. But this is again the reason, like they wanted to scale as much as possible on a single what you could do with a single GPU. And this is again meant for training very large frontier models. There are a couple of things that you have to keep in mind though, which are like, first of all, this is a very active area of research, so there may be like over, for instance, like we have like some ongoing collaboration with people in Austria that just released like a couple of weeks ago a different recipe from the NVIDIA one, which is called Quartet 2. And what they are doing there, they try to combine different approaches. So like some building blocks may be different, but this provided like some very interesting improvements over the NVIDIA recipe. Finally, another thing to keep in mind is that when we are referring to all these NVFP4 operations, we are usually tackling the linear layers of the model. And if you instead want to go for the attention kernels, these are usually some stuff that is still in development. So we will probably know more soon. But if you, for instance, want to try this out and go into the NVIDIA library, which is the transformer engine, you will find only the one for the linear blocks. So yeah, this is kind of a very interesting topic. It will be more and more influential because like there was a huge bet from NVIDIA and also other competitors into this low precision area. So for training, both training and inference. So it will be really relevant in the LLM architecture and provide like deployment of these large models. So this is everything from my side. I don't know if we have time for question answer now or later.
Great stuff. Yeah. No, this is perfect. And let's see. Someone asked about another format, Q4 underscore K underscore M. Are you familiar with that? How is it similar compared to NVFP4?
I'm not familiar with this
Yeah.
Q4.
Yeah, me neither. Okay. Let's see. A lot of comments here from my buddy Todd. Todd always brings with him a lot of good knowledge throughout the years. He's been in the Bay Area for a long time, and he's seen a lot of things. Okay, I think that's probably it. There might be one or two long tail questions here if you want to scan real quick. Otherwise, I know it's like, what is it, 8 o'clock your time, so feel free to drop. Any concluding thoughts? And then I can do a quick demo on the MCP stuff and OpenClaw.
From my side, like this okay, there is a we mentioned that NVIDIA is in transformer engine. That's a good question. There is for sure like some. The question is like there are other libraries using NVFP4. From my knowledge, there are like at least some research projects going on GitHub, like using NVFP4. I'm not sure there is like some kind of large and battle test library as a transformer engine, but one bad thing that transformer engine doesn't provide is the code to reproduce the paper results. So they are just providing you like kind of the building blocks on which you can wrap around your linear layers and use the NVFP4. I think AMD does not have anything similar to NVFP4. Maybe some stuff on post-training quantization for sure, but NVFP4 is something that NVIDIA came up and is like proprietary.
Okay.
Um,
All right. Let me just show a quick demo here. And if you want to keep answering, that's cool. Yeah, thank you, Riccardo. That talk was great. I guess, the other thing to discuss maybe on this topic real quick is the hardware, like the separate instruction pipelines and tensor cores and things, right? Which I think you touched on a little bit, but can you talk a little bit about that? Like, there's actually separate hardware that's capable. There's like different types of tensor cores, right? And they have separate
yeah,
pipelines.
that goes into the more into the kernel development, which is something I haven't like experimented much, but from my knowledge, what it changes a bit is that like First of all, there is this tensor memory that is like a different way of handling the results that the tensor core are producing. So like you are wasting less registers, you can store stuff there. And yeah, also like this different way of like having these two pipelines of operation that gets executed by the GPU. I'm not an expert on that. We have like some blog post coming on that, which will probably be published soonish on our website, which will cover both like the part I presented here on the slides, but also some current development that have been done by Daniel for one. There was like recently a GPU mode challenge on NVFP4 kernel, and so like the blog post will probably also explain more on like this hardware instruction, low-level hardware instruction that allows you to squeeze the performance of these GPUs basically when you are developing your own kernel.
Gotcha. Yeah, yeah. The kernel development side of this is what my book covers, and I've got a lot in there. I did put a link to the blog post in the meetup that you're referencing. Yeah, one of your peers
Yeah,
submitted, and that's a really competitive space over there. I'm actually kind of toying with submitting. There's one more challenge left from that series on group gems, and
and it's also
I'm
quite interesting to see there that like a lot of the development going on there has shifted into DSL languages. Again, like probably the best solutions are still using CUDA, but then like you can get like some quite good kernels already with the cute DSL that NVIDIA is kind of pushing recently, which is again Python, so easier to deal with than rather to write pure CUDA core code.
Yeah, for sure.
Yeah.
And I mean, up till now, to do things like that, we've either had to write CUDA C++ or we would use Triton. Triton was built by the folks over at OpenAI, and it appears that OpenAI doesn't yet use Blackwell because Triton's kind of lagged behind and doesn't really do some of take advantage of some of these things. So there's been a lot of new communities popping up like Helion and I don't know, the other things around the PyTorch community. And then of course the NVIDIA folks have finally decided to recognize Python as a first class um, uh, like right, like kernel, programming language. So yeah, like you said, QTSL, there's Qtile, there, all kinds of things that give people more options. I feel like they're all at kind of different stages of maturity. So I still write CUDA C++ just because I know I can get to everything, but it's nice to see Python becoming first class citizen. Yeah.
Yeah, kind of
Um,
for sure lowers the entry barrier for like new people to develop new kernels, which
yeah.
is probably another like CUDA mode for NVIDIA in some sense because it makes easier and like opens up the contribution for like larger slices of the community there.
Yeah, yeah. And, my experience, I think I was talking with Mark Sorafin from the GPU Mode, the guy that actually hosts, all these competitions. He had a chart that showed, I think, like a very large majority of the submissions are still CUDA C++, like the ones that are winning.
Mhm.
And Triton for these competitions almost never shows up. And there was a middle ground of cute DSL and things, but it seems like the folks that at least right now that are winning these types of competitions are still using CUDA C++, which made me a little or steered me because I was going to use this opportunity to get more hands-on with these like Python libraries. But I was like, well, if I have any chance of actually winning this competition, I have to stick with C++. So there's some cool prizes here. I think first and second prize get a ticket to next month's GTC conference here in San Jose, and that's worth, I don't know, that conference is crazy expensive now. It's over $2,000. Um, which actually is a good segue into next month. I know we're about 10 minutes over here. So next month, we're going to have, I'm going to do a recap. This is my favorite conference of the year by far. Yes, every year I've gone as far back as I can remember. I've spoken there a few times as well too. And we're also going to have a talk on deep dive into flash attention and kind of how things have evolved. Flash attention, sort of the hello world of software, hardware, co-design when it comes to like LLMs and the modern Blackwell GPUs and how we're like taking um, how we're really pushing performance by building software that has mechanical sympathy in mind and knows how the actual hardware works. So get a deep dive there by my buddy Seth Weidman. And then I think we've got a bunch of talks coming up, like a lot of great stuff. Actually, last month we weren't able to get to a talk. So we're going to redo that one, I believe, in April, I think. So, and then, yeah, real quick, let me just show folks, just to check the box here of, the MCP and the OpenClaw stuff. So here's an example where I just, here's my files here. I've got some kernels. These are all the kernels from the book. I think I chose chapter 9. And all you have to do is, drag and drop like a particular file here. Which one did I do? FP4. I chose one of these, dragged and dropped it over into here. Boom, 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 right there, and had it profile and then optimize. And then this is MCP kicking in here. These are, the MCP tools that I built that support the book and are tuned for, Blackwell. Actually, yeah, they could be used for like anything because it'll inspect the current environment. Now, keep in mind that I'm I'm cheating here in the fact that I'm actually on a B200, and this is thanks to the Verda folks, specifically Paul over at Verda. So I'm operating within. I use Cursor and VS Code right now because I can SSH into the actual hardware that I'm trying to optimize for, and that's a game changer because otherwise you're on your MacBook trying to write CUDA kernels, but you're not able. There's no verification loop in the process. So this is actually running MCP targeted on the actual hardware. It's benchmarking it. These are all the MCP calls and JSON responses going in and out, or right, like coming back. And this is actually using the NVIDIA Insights compute, and it's doing deep dives, and it's actually running the kernel, and it's tracking all the GPU counters that it can extract that the GPU exposes. It's taking a look at those. And actually I've got the book in context here as well. So I have a PDF version of the book. I converted it to Markdown just to make it a little more LLM friendly. And it's actually using parts of the book as sort of a RAG like way to give hints. It's still really hard to find tuning information in one spot, which is why I wrote the book. Like previously I had to go to Twitter to get some threads that on performance optimization, or it was just tacit knowledge in people's heads over various blogs somewhere behind Substack paywalls, all that stuff. So I've brought it all together into these 20 chapters and then made it available to us mere mortals here through MCP. And then something else. So this is basic MCP. So it ran the benchmark. It's found. Let's see. Oh, actually, this one appeared to time out, and yeah, some other things. Yeah. Anyway, so that's yeah. I would say that MCP is like last year's news. Now we're all into OpenClaw and the ability to actually, from WhatsApp or from my text message or from anywhere, I can run and control and perform optimizations from my WhatsApp channel. So here I've got a WhatsApp group that just has me in it, me and my bot, my OpenClaw bot, and I give it commands. And this way, the whole last year, I was pinned on my computer, constantly watching and, like constantly tweaking code and like doing all kinds of things. Now I can run these optimizations remotely while I'm at dinner or at the gym, and I can get the output and I can tell it to, try a new technique or to look up the book. And, yeah, so again, just to kind of come full circle here, I have decided that as of January 1st, 2026, I am never writing a single line of code again. I'm only using my agents, and which sounds kind of ridiculous, and people have some thoughts on that, but I've got other shit to do. Basically, I've got higher level stuff to work on, and so while this thing's churning away, and so yeah, this is all using like the OpenClaw, which is pretty fun stuff. And yeah, if you haven't tried OpenClaw, give it a try. Getting it to wire up with your GPU, because again, this is a remote GPU, and so it has to shell out there. It has to have Codex or Claude installed out there. It has to be authenticated. So there's a little bit of setup, a little bit of messiness, but with this OpenClaw harness or framework, which actually the guy just joined OpenAI, I think this weekend. So yeah, OpenAI basically is hopefully going to keep OpenClaw open, and lots of big community. But okay, yeah, everyone, thanks a lot. We will see you next month. Let me just double check for last minute questions. Yeah, a lot of automation. Anyone who has DevOps tendencies is going to jump all over OpenClaw because there's a ton of automation. And yeah, Riccardo, thank you so much, man. We will
Yeah,
be
thanks a
in
lot.
touch.
Yeah.
Yeah, are you guys coming to GTC by any chance?
I think some of us will be at GTC. I think Paul probably will be there. So
Oh, great. Okay, cool. Yeah, I'll ping
yeah,
them and make sure that we get to meet up. So awesome.
yeah.
Yeah, thanks
See
everyone.
you.
Yeah, see you next month.
Thank you. Bye.